Kill it, kill it. Oh, wait.
Yep, I built that. I'm gonna tell you exactly how I did it. First things first, I should probably start with, do not try this at home. I'm not a professional, but I was very careful, and I don't condone you doing this. For the purpose of this video, we'll go over how a rocket engine works very simply. If you want a better in-depth look, I highly suggest a personal favorite of mine, Everyday Astronaut. He's made fantastic videos. They go super in-depth with how rocket engines work and the physics and the math and blah, 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 blah. I highly, highly suggest it. There are two main ingredients that go into every rocket engine, a fuel and an oxidizer. The fuel and the oxidizer mix within the combustion chamber to combust, creating hot gases that then are forced to escape through the path of least ambient pressure. That's usually on the outside of the engine or the other side of that bell nozzle. Those hot gases are then forced to converge down on a single point called the throat. The converging style compresses and maximizes the velocity of those hot gases, which then expand and diverge through the divergent point of the bell nozzle, creating that flamey effect or thrust that you will see on the outside of a rocket. Now that we have a basic understanding of how rocket engines work, let's talk about the three different kinds that exist. There's solid rocket engines, which basically mean that both the oxidizer and the fuel are in solid state. The second type is hybrid, and that means that the fuel is in solid state and the oxidizer is in liquid state. Finally, you have liquid engines. These are the most common ones. These are the ones that you would see Raptor, so SpaceX use, or NASA on the space shuttle and the Apollo missions. These are the most common ones, and it's basically when both the oxidizer and the fuel are in liquid state. So now for the question that you've all been wondering, what did I make? I made a hybrid rocket engine. I know, thank you. So how did I plan this build? First, I started off with all the theory, which involved a lot of reading and a lot of Googling and finding fantastic websites like Nakka Rocketry. This website helped me understand the solid rocket motor theory and nozzle theory that I needed to build this rocket engine. This website helps you find your stagnation temperature, your local sonic velocity, your Mach number, and your stagnation enthalpy. You need all this to figure out the exit velocity of your nozzle. This website also helps you find the nozzle design condition that is required to figure out the ratio between the area of the throat to the area of the end of the divergent nozzle. This is also called the optimum expansion ratio. Since the engine I built was not going to be used in space, it's not in a vacuum, I assumed that the external ambient pressure would be 1 atm, which is 1 atmosphere, which is pretty accurate, off by a little bit, but that's fine. The chamber pressure for my rocket engine in this case would be dictated by the amount of pressure that I could get in an oxygen tank from Home Depot. Pretty simple. There were also a bunch of research papers that I read and YouTube videos that I watched on other people doing these rocket engines using the same sort of fuels or just sort of designing the best bell nozzles. I'll include them all in the description down below. I will not bore you with it in this video here. Now we're getting on to the design portion of the engine. As with any design, there were a couple factors that I wanted to include. I wanted to be able to dismantle it and relight it as many times as I wanted. The design had to be simple enough that I could machine it in my own garage. Majority of the parts that I use had to be off the shelf since I don't have a CNC router or some other machining tools that would allow me to make custom components. I was relying on step drill bits from a local hardware store that sort of fit the expansion ratio that I was going for in the bell nozzle. I knew I needed fire gaskets to be able to contain the hot gases inside of the combustion chamber. Because of course, if you have metal on metal contact, there's a lot of microstructures that allow gases to escape and will ultimately make the engine fail. And this is a look at the final design that I settled on. Now I knew that I needed material that could withstand two main things, the stresses from the combustion and the heat from the combustion itself. The two main stresses I was worried about for this design were the hoop stress involved with the combustion chamber, which would be the outward stresses on the tube that would be fighting against the ambient pressure on the outside, pushing inwards. The other one I had to be worried about was linear stress. This would be felt most on the bolts that I intended to run across the side of the engine that were holding the two pieces, the two caps around the combustion chamber from popping off. In terms of heat, the thing I had to watch out for most was the thermal resistance of the materials I was using. Now, normally on a bigger rocket engine, one that was professionally made and professionally used, they have heat exchangers running on the outside of the divergent nozzle. In my case, I didn't build a heat exchanger because that's very complex and would kind of defeat the purpose of my design. So what I did was I added a lot more material on the outside of the engine. Now, of course, this has a major drawback. If I ever did want to launch this engine, it would be stupidly heavy and it probably would not have a very good thrust to weight ratio, which kind of defeats the entire purpose of an engine. But in the case of what I was trying to do, which is just static fire it, it was fine. And I knew it would withstand the heat and it wouldn't melt or drip or anything like that and ruin the ultimate design. Having said all that, I decided I was going to use aluminum because it's relatively cheap and it's very, very strong for what it is. So I used one of my favorite websites for my degree and I picked the type of alloy that I wanted to use for the rocket engine. Now that we had all the parts, it was time to machine the metal. Now this started off very smoothly because I had already done all the calculations for exactly where the screw holes had to be and the nozzle for the oxygen tank. I had all that designed and I put that onto some painter's tape and I just machined through that. That was no problem. The problem came when I started doing the nozzle. I had a drill press that I bought on Kijiji that was half horsepower. It worked great, it was 50 bucks, I had no complaints for the cap. When it came to the nozzle, the torque was just not high enough. And I'll explain how that worked using this. Torque is the force that is applied at a single point to spin a lever arm. That means that if you have a lever arm of length R, you will apply a force of F. That also means that if you increase the length of the lever arm by 3, the force will decrease to 1/3. Putting this into terms of a formula, you have torque is equal to the lever arm length R and the force multiplied by the angle between the force and the arm. Now, assuming torque stays the same, we have the exact same formula with 3R because the length of the lever arm increased by 3 times. We have 1/3 the force and sine theta. Now, simplifying this, if we just cancel out the 3, we will see that it's the exact same formula. Of course, the force that is being applied is at 90 degrees, and if we look at a quick sine graph, we'll see that 90 degrees is just equal to 1. Thankfully, my friend knew somebody with a bigger drill press that was able to just complete the drill for us, and we were off to the races. Next, we threaded the piping for the O2 tanks. We threaded all the little screw holes for our bolts that were going on the outside of the engine. And finally, we made our fire gaskets, as I alluded to before, using parchment paper and a fridge. Finally, we created the fuel. Now, this was actually kind of cool. What you do is basically you get a piece of Pyrex glass. I used a little measuring cup, filled it up with paraffin wax, and I put it in boiling water on the stove. I would then stir it and help it evenly melt. And then once it was fully melted, I got my little combustion chamber. I put a little bit of parchment paper, some ice on the bottom to help it cool once you pour in the paraffin wax, and I began to pour to fill up the tube. Once the tube was fully filled up, I put it in the freezer and I let it freeze for about 2 hours probably. Finally came the assembly. Now, all this was actually very easy, thankfully, because of the design I made, which just basically used those bolts around the thing to hold everything together. So what I did was I got my little combustion chamber of paraffin wax out from the freezer. I put a little hole through it using a drill bit that matched the exact same diameter of our piping for the O2. And I put it all together, I put the fire gaskets in, tightened it up, and we were ready to go. Now for the fun part. We lit it up. That was pretty cool, but you probably hear me saying kill it, kill it, kill it in the video and screaming it pretty loud. This was actually because I thought that I had screwed up my optimum expansion ratio, which we spoke about before. Because what ends up happening if you screw that up is the flames will end up either over diverging and going sort of on the outside of the bell nozzle, or they will under diverge and they will kind of go inwards. So I actually thought that I had screwed up and it was going inwards too much. Little did I know it just had to warm up a little bit, and it really did light.
Holy shit! Holy fuck! Go!
Anyway, that's basically how I made this, the rocket engine. Thank you very much for watching. If you liked it, I would appreciate if you could subscribe. I do a lot of software and mechanical engineering, and I'll be making a lot of videos in those sort of two realms of existence. So if that's the sort of stuff that you like to watch, I would appreciate if you could subscribe. Anyway, thank you for watching. Have a great one. See you later.